Now let's talk about circles. You may have noticed in looking at irregular polygons that when we look at regular polygons with more and more sides, they become more circular. So how do we define a circle? Some people think of it as a polygon with an infinite number of sides. There's so many sides it's become curved. Now, as you found in our exploratory activities, there's another important way we define a circle. It's the set of all points the same distance from some center. Now, why does it matter that we define that as a circle? Well, sometimes we'll draw this and say, yeah, that's a circle. But that's not a precise circle. My little potato here, it's not all the same distance from one center. So when we define a circle this way, it allows us to draw circles in a more accurate way and then use those to help us solve problems, as you saw in your exploratory activities. Let's actually take a look at some of those exploratory activities and other fun things we can do with circles. All right, let's first look at the prisoner escape problem. We're told that there's a prisoner who's escaped from this prison here at point P, and they've been on the run for 45 minutes, and they estimate she can move at most 4 miles per hour. Could they have reached the swamp yet? What about the woods? Well, if they're going 45 minutes, that's 3/4 of an hour. And so I can do 45 divided by 60 times their speed of 4 miles per hour. And it looks like the most she could have gone is 3 hours. Or excuse me, 3 miles. My scale tells me that each one of these boxes is a mile. So I'm going to make a circle that is 3 miles in radius. That means the prisoner should be somewhere inside this circle or at its edge. So the prisoner could have reached the woods, but not the swamp yet, because there hasn't been enough time. There isn't enough distance, or it's not inside this circle. This idea of using circles to locate things is used a ton in real-world situations, which is one reason why we teach circles in K-12, is because when people understand what makes a circle, it makes it really useful. Let's switch now to the buried treasure. So we're told that a buried treasure is hidden somewhere near the cool rock and old tree on this map, these 2 points. A secret treasure map says that the treasure is 70 feet from the cool rock and 40 feet from the old tree and is either in the nearby swamp or nearby woods. Where could the treasure be? Well, we're told that this length is 50 feet, so it looks like each square is 10 feet. So cool rock, it's 70 feet from there, so I'm going to make a circle 1, 2, 3, 4, 5, 6, 70 feet. And so just looking at this, it could be in the swamp or in this tiny corner of the woods. So we need to do the old tree to figure out for sure where it could be. And then it must be 40 feet from the old tree. 1, 2, 3, 4. And now since it's a circle, I know that if I go out 40 feet in this direction, it's going to get 40 feet in every other direction. So it looks like my treasure could be here in the swamp or here somewhere. We'll say this is in a field, but we're told it's either in the swamp or the woods. So this must be where the treasure is. Now notice without that extra clue saying it's in the swamp, we wouldn't have enough information to say where they are. The treasure could be here in this field or in the swamp. That extra bit of information is needed. So if I want to find a location of something using only circles, saying its distance from various points, This tells me I need 3 distances to narrow in on a point. This is one way we use the word triangulation, where we say 3 circles give us enough information. And we see that especially in earthquakes. So we're going to find where an earthquake occurred. Now, some of you may remember from geology classes that when an earthquake goes off, when an earthquake happens, there are primary and secondary waves. And the time between those primary and secondary waves can help us know how far away an earthquake is. So let's use that here. So this seismograph, we have seismographs at these 3 monitoring stations, and they tell us how far away an earthquake is. We don't know where it is, but we know how far away it is. So we know there's an earthquake that station A records is 130 miles away. So it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Each box is 10 miles. So I'm going to start a circle at circle A. And I'm going to go out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So earthquake could be anywhere on this circle if we only use our knowledge of station A. Let's see, station C says it's 170 miles away. So if I start at station C, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Now with these 2 circles, we have 2 possible places for the earthquake. These 2 points right here. And the question is, which one is where the earthquake is? Right now, with just station A and C, we don't have enough information. We need to use the 3rd station, station B, which says the earthquake was 100 miles away. So I'll just count down 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And hey, we have a winner, winner, chicken dinner. This point right here is where the earthquake happened. And that's one way we use circles. GPS works in a similar way, where you may, on old GPSs, it'll tell you how many satellites are connected, and you need so many satellites to have a good connection. So satellites work in a similar way to say this is your location, though I believe you need 4 satellites to get a perfect connection of knowing exactly where you are, including elevation. So I hope this was helpful and you're thinking of circles. Good luck on the homework.